Hi, everyone. It's a pleasure to come virtually to speak with you a bit today. And thanks for the invitation from Darby and Shawshank and a few others who reached out to me. So I'm Shaheen up here in Boulder, not too far away. In the electrical engineering department. My background is more in physics and material science. I'm part of the Renewable Energy Institute here as well. So I'm going to tell you a story about some recent interests in reservoir computing, both in theory and optimization, and also a bit in the physical implementation of these systems. And I hope it relates to some of the COINFLIP efforts. I'm not super familiar with everything going on in COINFLIPS, but maybe it could start a discussion and could lead to further, ideas down the road. So I'll hopefully keep this informal. If you do have questions, please raise a hand, throw up in the chat, and feel free to interrupt me. So just a broad background. I'm sure you're certainly familiar with neural networks, and many of you also in reservoir computing. But the first question is, what is the reservoir computer? And I think the simplest picture is that you take a standard feed-forward network and scramble the connections, and you have a randomized network with a single layer of output that you would train. And the reservoir constitutes a nonlinear dynamical system that you train to map onto another system, the physical system that you really want to understand. So there's a couple of advantages because there is a single output layer. It's very fast to train it, and importantly for us, very energy efficient. I'm sure you've heard some of the numbers required to train large language models, GPT-4 and so forth, that this is a month of training and $1 million, and many kilowatt hours are spent, which is increasing concern just for maybe climate impacts of AI down the road. So energy efficiency is a big part of this. Another advantage is that they are very well suited to time series analysis and data and prediction, and in many cases can outperform feed-forward networks, or convolutional neural networks, autoregression trainers, and so forth. It's still an open debate which architecture would be the best for time series data, but reservoir computing is in contention. And then lastly, when we go to implement them in a real physical system, kind of the field is wide open. People have done this with FPGAs. You can do this with ionic materials. I'll show you in a little bit. Examples include balls and springs in a large mass of a mechanical system that could be a reservoir. In fact, here that is. So, example implementations, people have made mechanical systems, with balls and springs. And as long as you have sort of nonlinearity built into the network connections, then you have something that is a reservoir. A little more device-y type implementation would be a network of carbon nanotubes. And here you just lay down a random array of carbon nanotubes, and each junction between the nanotube is effectively a synapse or a weighted connection between neurons. And the point is that once you build the physical reservoir, the connection weights are built in, the network topology is built in, and then you don't touch it anymore. There's no training, no alteration of that system. So it's as if you walk up to a physical system, which is a highly dimensional nonlinear thing, and you plug in some probes to it, a small number of probes, and you automatically have a reservoir computer. In that sense, many different systems could be used for reservoir computing. It's almost magical. You could look around the world and find lots of things that are actually reservoir computing. And it speaks to the idea of computing closer to the physics of a material or in material computing. And that's kind of a broader theme that I won't have a chance to talk about, but that's the general idea. You can now buy these things commercially. There's the company Innovative Quantum Solutions, QCI, and they claim to sell the first commercial reservoir computer, which is a little standalone box that you plug in as a coprocessor for your computer. This is again FPGA based and is tailored for time series analysis of things like the Lorenz attractor. I'll talk a lot about today. Other nonlinear dynamical systems that exhibit chaos, including the Mackey system, the Ressler attractor, and so forth. So you can go and buy it. Of course, it's going to cost a bit of money. You could just as well get an FPGA, download the code off of GitHub, and get up and running. And that's probably the easiest way to do a physical system right now. Oh, I'm not endorsing or not endorsing the company, but I'm just noting that it's available. And then if you are coming from biological background, and I think many of you in COINFLIPS are, you're probably aware that there are models of biological brains that look very similar to reservoir computers. So I just picked a random paper 6-7 years ago that some of the dynamics in the prefrontal cortex appear to mimic what we would consider a reservoir computer. And the way they came to that conclusion was they programmed up a simulation of a reservoir and trained it on multimodal stimuli that would be fed into the prefrontal cortex, and found that it behaved in similar ways according to some of the readouts that they could measure from the biological brain, probably a mouse or a rat in this case. So their claim is that reservoir computing is a pertinent framework to understand local cortical dynamics in higher cognitive function. No one is claiming that the entire brain is a reservoir computer, but there are certain regions that have similarities. That the neurons are in somewhat of a symmetric connected cluster. It's not so obvious what's forward and backwards. And you have this property of nonlinear connections between the neurons. So something I think interesting to think about. Okay, so let me talk a little bit about some of the math behind these and ways to improve the performance if you are trying to do something like predict a chaotic system. So the kind of standard chaotic system is, for this purpose, is the Lorentz attractor, the Lorentz system. It has three differential equations in 3 dimensions, X, Y, and Z. And you've probably seen this before. You get 2 attractors in the system in XYZ space, and it forms this butterfly, right? So if you start at some initial point and you carry out the dynamics, then you will cycle around one of the attractors for a period of time, but then you'll flip to the other attractor. And the flipping back and forth is a chaotic process, right? Historically, it's very difficult to predict. And so what we do is we simulate just in Python or Julia. Increasingly, we like Julia. We simulate the real system and feed it into the reservoir computer. Then we train the single layer of outputs over 3,000 or 4,000 time steps. And then we turn off the input, and we have a feedback connection from the output back to the input. So it becomes an autonomous reservoir computer at that point, that the only input is the output. And that allows the system to carry on into future time and predict the chaos into future time. And it does this very well. So example down on the lower right are those X, Y, and Z coordinates. So t equals 0 here is the moment that we turn off the training signal and we're fully in the inference or prediction phase. And you can see along all axes that and the units here are called Lyapunov time units. So lambda would be a Lyapunov time unit, right? And the Lyapunov exponent is the characteristic time at which 2 points that are very close in phase space diverge exponentially as we go forward in time. So if you're just guessing, if you're just predicting randomly, you wouldn't expect to do much better than a single Lyapunov, the 1 on this time scale. And in this case, you can see it reaches 9 or 10 pretty easily before the predicted and actual values start to diverge. And what you see is that in the X and Y dimensions, the divergence is in the form of, well, the system went down and the prediction went up, or vice versa. Because it has this butterfly property, the way the prediction goes wrong is it goes to the wrong side. It went to the wrong wing of the butterfly. That's less evident in the Z direction, and the Z direction doesn't have that axis of symmetry. So anyhow, you can see that the predictions are quite good. This field was largely started by Ed Ott at University of Maryland, and there was a lot of press about this. And he claimed that this was the best system that we know of for predicting chaos. I don't know if that's entirely true now, but it's certainly very impressive. Okay, so a key part of this, and what I'll focus on for a few slides here, is the role of the activation function. So what is the nonlinear component of each individual neuron in the reservoir? So that's a bit of an eye chart, but let me just go back and say that for each point in the reservoir, and this is a picture of 300 neurons in a reservoir, they are connected randomly to their neighbors, usually with an average connectivity of six neighbors. That turns out to be close to optimal, but each one is running a nonlinear activation function, and they're all running the same activation function. So we're not assuming any polydispersity in those activation functions. So typical ones would be something like a hyperbolic tangent, that has a built-in nonlinearity. That can be a hard version or a soft version, or asymmetric versions of that, like a CELU or a ReLU, things that are used in normal machine language activation functions. Now, one interesting aspect here is some of these functions have a degree of curvature, and I'll point your eye to the swish function, and also potentially non-monoticity, right? That the y value does not equate to necessarily a single x value. That turns out to be useful, and the degree of curvature turns out to be important, a thing I'll show you in a moment. The other issue is that curvature needs to be placed in the right position, that the curvature and the nonlinear part. If it is off from the running region of the system, that the system is missing that activation region, the nonlinear region, the forecast horizon goes down. So it's important to position that nonlinearity in the right place. And I'll show you an example of that in a second. So here's an optimization. This is kind of a hyperparameter optimization, if you will, of a activation function called the swish, right? So this is an asymmetric nonlinear with a bit of curvature and a bit of non-monoticity here. And there's a free parameter beta that changes the function from fully linear at beta equals 0 to something with a non-monotonic curvature near 0 for beta equals 1. So the beta gives us a nice knob to tune the curvature of the activation function. This relates to the information content of that activation function. Clearly, if it's linear, then there's no information or none that can be applied to the reservoir. And as it gets more complex, and we'll talk about entropy in a second, if there's more entropy built in, then it can potentially perform better. So one can do a global optimization. This is a plot of that parameter beta, and in line with the size of the reservoir. So clearly you expect a larger reservoir to perform better. Although there are caveats, you have to optimize other parameters like a ridge regression parameter and the training time. So you have to do all that. But if you fix those other parameters, what you see is this sort of ridge that's developed of high performance. So the blue color here is forecast horizons of 10 or 12 or 13, which are very good values. And you see, if you tune the beta, you can actually get these very good values for quite small reservoirs. So one could have a reservoir, maybe a couple hundred neurons large, and if beta is optimized, then you could still get very good forecast horizon. So practically speaking, in a physical system, we'd like to use smaller number of neurons. It's easier to implement. It would be faster to train, more energy efficient. And this tells us that we can do that if we've optimized the curvature of the system. Now, of course, there are 5 or 6 other parameters that you would want to do this with. And so we're not claiming this is a global maximum. In fact, we can do better, but this is an example of at least one parameter optimization. Well, 2 parameters. We can do that as well for a hyperbolic tangent. In this case, the parameter that we're changing is the position of the hyperbolic tangent along the x-axis of the input of the neuron. And so we're just shifting it or applying a bias to that hyperbolic tangent. And same deal. So actually with no shift, you can get good performance if you have a very big reservoir, but then you can do pretty well as well for smaller reservoirs if you shift it. In this case, it's symmetric. You could shift it plus or minus some amount and also get good performance. So again, optimize the activation function and you can get away with a much smaller reservoir that maybe is easier to physically implement. Now, we kind of started this process thinking that the activation function has some information built in the form of some entropy. You can apply other thermodynamic properties, like you can ask what's the temperature of a curve. There's a nice paper that asks the question, what's the temperature of a curve? And once you have temperature, then of course you can get lots of pseudo thermodynamic properties from a function. So the more obvious one would be some form of entropy, state entropy. You can do that for the activation function. You can also do that for the whole reservoir by basically carrying out this operation, a logarithm of the difference of activations of each neuron applied to a generator function, which is a Gaussian. So you assume that there's some inherent Gaussian distribution in the system. You apply that generator function and then do a sum over all of the possible connections in the network, and of course take the log. You could do this at each time step to get an instantaneous entropy, and what you find in most systems is that instantaneous entropy mimics the dynamics of the system. So the whole system, or let's say the X position goes up in value, that the instantaneous entropy can also go up. So this is kind of a mimic for what's happening in the system. That's kind of interesting. Moreover, you can just average this over time. So in this case, the yellow here corresponds to the prediction up until the forecast horizon. So at that point, the forecast deviates from the real system, and then the rest continues. It turns out that we were hoping that there would be a discontinuity in either the instantaneous or the average entropy at that point. There isn't. It basically turns out to be the same. So it's not a quantitative predictor of the forecast horizon if you look at it instantaneously. But if you take the average value over a population of activation functions, so for instance, the hyperbolic tangent, where we are changing the shift to change that activation function, or with that bi-switch function, we're changing the beta value, then you do see a pattern that emerges, a correlation that emerges. And what you see is that for very low entropy, that the forecast horizon goes to zero. In this case, you would have to go to much lower, to zero. You would see it goes to zero. Then there's a fairly gradual rise and then a peak. So there is an optimal entropy. And we looked at a lot of systems, and it tends to be around between 0 and 0.5, or in the vicinity of 0.5 is an optimal entropy. After that, there's a steep decline. So if you have too much entropy, the system is too complex, too complicated. It's unable to capture the dynamics, at least for the Lorentz attractor. So the conclusions are that there does appear to be optimal entropy for the system, and it's not predictive of the forecast horizon for a given instance, but there is an overall trend if you look across versions of a given activation function. And then just generally, you want to be below a threshold value of around 0.5, after which the performance really drops. So, this is just kind of an initial investigation, and it suggests that one could look at the thermodynamics of the reservoir as a proxy for how it can perform. And I like to think of it as maybe a patient in a hospital bed, and you've got the cart next to it that's giving heartbeat and blood pressure and all that, that one could have a neural network, in this case, a reservoir, and be monitoring these thermodynamic variables as it operates. And that could give you some clue as to the function of the reservoir. Anyhow, we are submitting this probably later this week to a journal of physics and to the archive, so you can look for the full paper hopefully quite soon. Maybe I'll stop for just a second. Any questions emerge?
We do have one from the audience, from Felix, who asks, is there anything you can comment for spiking reservoirs?
Yeah, so I should have mentioned the work I'm doing is non-spiking, and clearly that opens up a new space. In my mind, the motivation for spiking is energy efficiency, right? So you're using less energy per pulse, but also gives you access to other biological functions like spike timing dependent plasticity. So, we are still in the mode here of the network has its own internal dynamics, and we don't really care what those are, and we're going to use that as the information reservoir to run the system. If it was a spiking reservoir, presumably that would give you much more dimension of the information. So I am a big proponent of that. We haven't simply gotten there. There's enough to talk about just in terms of DC operation.
Thank you.
Okay, so let me switch gears to the second part of the talk, which is how we might implement these in at least one physical system, that is organic electrochemical transistors, or OECTs. So in this case, we're going to assume each one of those nodes is an OECT device that is based on a conductive polymer immersed in an electrolyte, has one source and drain electrodes, and possible multiple gates that each are connected to neighbors. I see another question from Shardeep. The entropy rate of a dynamical system can be measured using Kolmogorov-Sinai measure. Yes. So we've just used, a very basic measure of entropy. You could think of a whole class of different measures of complexity. This one worked surprisingly well, others not so well. So I think, there could be a more deep exploration of what exactly is the right thermodynamic variable. So, once we had temperature, you can also get pressure and an analogy for volume. It turned out that 1 over pressure volume works pretty well. But then the average state entropy actually did better. So yeah, the Kolmogorov stuff I think would be also interesting. Thanks for the question. Okay, so if you're not familiar with OECTs, this is just a one-page primer. And the idea is that you have something that looks like a conventional MOSFET transistor with a drain, a source, and a gate. But the conductive channel is not silicon or gallium arsenide, but is a conductive polymer, usually polyethylene dioxythiophene, PDOT. And then this is immersed in an electrolyte. Electrolyte, very simple. It can literally be table salt or KCl, a very simple salt bath. Then there's a gate electrode that's also immersed in that liquid electrolyte. And the point is that when you apply a gate bias, you are driving one of the ions through the liquid medium into the conductive channel. And that will either dope or de-dope the polymer. We oftentimes run these in depletion mode. So it's a doped polymer that we are de-doping with the ion migration. So this gives you a way to modulate the conductivity of the channel, through ionic motion induced by the gate. And it turns out that the advantage here is you can get away with very low gate voltages. So tens of millivolts, even microvolts, can be sufficient to alter the conductivity of the channel. That gives you a very high change in conductance for a small change in voltage. That's called the transconductance of the transistor. And you always want a large transconductance. These devices have among the largest transconductances of known transistors. I'll point out, and I think some of you or maybe are in the audience, that there is related work that's been done here or there at Sandia in collaboration with Stanford and Alberto Soleil's group. So this is not entirely new. There's already been some excellent work along these lines. So in this case, the device was not exactly the one I pictured, but has PDOT in different locations. There's some PDOT on the gate, and it's termed an ionic floating gate memory. I think if Conrad's in the audience, I'm not doing a very good job describing your work, but so please forgive me. But this was used to make the memristive connection in an array that then could be used in any neural network for classification. And they used it to build an exclusive OR gate, which is the one you want to start with. If you can do exclusive OR, you can do many others. More recently, there's been work out of Dresden, TU Dresden, a group of Carl Leo, and they showed examples where you could just put down the polymer in a dendritic pattern. So they used electrochemistry to deposit the PDOT polymer and connected to a multi-electrode array. You can tell we're already doing neuroscience because it looks like a multi-electrode array. And in this case, the just random connections and random topology of those dendritic polymer chains formed the reservoir network, so formed the topology. And then the flow of ions into and out of the channel was a way to modulate the connection weights. So they built this, and then they integrated it into a flexible plastic and wrapped it around the finger, and were able to measure your ECG and classify heartbeats using that simple device with quite good accuracy. So 90% and above accuracy. So this is a nice example of a pretty simple physical system, not a hard thing to build. And if you're smart about the training and the data processing, you can get a real, computational benefit out of this. They didn't talk about power consumption, but I assume it could be, quite low in this kind of device. Okay, so, one of the things that we are thinking about is going back to maybe a more conventional device geometry that you would print with lithography. What if you have multiple gates attached to the electrolyte, and each one of those gates goes off and attaches to another OEC device? What could you do with that kind of thing? Now, this brings into question, what is the total gate voltage that's generated by some combination of inputs of the individual ones, in this case, G1, G2, G3. So to first approximation, you can assume that that function is linear, that the total gate voltage is just the sum of those individual ones. And we've done some preliminary tests, and that assumption holds pretty well. As long as those gates are symmetric and close together, then G is a linear function. But I think you can make it nonlinear if you were to space those gates out and use more complicated geometries. Then you could tailor the G function to be something more nonlinear and maybe look more like a real neuron. So we think this is a pathway to really simulating a biological neuron. But before we get there, we could do interesting things even with just a linear combination of those gates. So in this case, we've made something, this was published a couple of years ago in MRS Bulletin, which we're calling a neuroboolean circuit. And the point is that your computational device operates in different modes at different length scales. And the smallest length scale would be a neuronal one, where in this case, we could have an array, or if you want, a reservoir of 5 transistors, 5 OECTs, that it's operating as a very small neural network to produce a Boolean function. And in this case, we also did an exclusive OR function made from these 5 OECTs. And in this case, we're making use of the multi-gate property just with 2 gates. So the second layer here, each one has input from the 2 devices in the first layer. So there's 2 gates coming into each one of these. And there's tricks to this in terms of where you hang the resistor off of the drain or the source, case 1 or case 2, and that gives you some design freedom in that circuit there. So we simulated this using standard transistor equations for the OECTs, and would train the weights in silico and then run them in this simulation to see if we could indeed get various Boolean functions. So I mentioned we could do the exclusive OR. We did also AND function and OR function. And like, for instance, you could put in 0.5 volt into one of the inputs and then get something close to 400 millivolts for one of the outputs to indicate a 1, or something of close to 100 millivolts or 0 to indicate a 0. So it's not a perfect differentiation, what we would consider digital logic. But if you had some smart electronics afterwards, you could turn this into a true digital system. So we think this could have merit, this neuroboolean idea that it's neuromorphic at the smallest scale and then Boolean beyond that. And therefore, you could use all your tools for digital design to make your computer. This does scale, so you can do larger circuits. So we, made an adder circuit with multiple exclusive ORs and ANDs and ORs, and also the truth table works out pretty well. It's not perfect, but red indicates a 1 and blue indicates a 0. And I'm sure it's a lot of fun to be looking at truth tables on a Wednesday morning here. You can have more games. So we thought it would be fun to do some reversible logic. So the double Feynman gates and the Toffoli gates, once you have the exclusive OR, that opens up a lot of possibilities. If you're not familiar with reversible logic, the idea is that you're not losing any bits between the input and output, right? So we have 3 input bits, 3 output bits. There's no loss of information. In principle, if you want, you can run it backwards. And there are arguments if there's actual benefit to that. Maybe yes, maybe no, but at least we show we can do that. And again, the truth table kind of works out. Okay, just to hit upon energy consumption considerations a little bit. The goal here would be to run this very low power, of course. Now, I didn't mention, if you're familiar with OECTs, the trade-off is the speed, that you're relying on ionic motion for ions to traverse the electrolyte to get into the channel. That's going to be a slow process. So these things are not going to be gigahertz devices, but probably in the megahertz to kilohertz. Could be quite slow. But that's okay, of course, if first of all you're making use of massive parallelism to get a lot of computational power, and the energy per individual computation is also very small. So we can just estimate this using some typical values that depends on the function, but you would be running in this case, sort of nanowatt to microwatt regime. This would be for a fairly large device of tens of microns in scale. So this is not a really nanoscale device. And then you ask the question, what's the bandwidth you're going to run this at? So, a very conservative and you're probably thinking ridiculously slow value would be a few milliseconds for the time constant, right? So this is a kilohertz device or even less. But this would give you a couple nanojoules per computation and averaged across these three. It actually varies quite a bit if you're doing, depends on the input and output, but a typical value would be a few nanojoules. Now, there are pathways to get that much smaller. So the first pathway is to increase the resistor values. And in what I showed you, we were using a couple mega ohms, but if you could go hundreds of mega ohms or even giga ohms, then those energy values go down, of course, because of ohmic losses are reduced. And then the second would be just run at lower voltage. If you could run this at a few tens of millivolts, then you could get down to very low energies per computation, so something below a femtojoule. We haven't done it, but this is just an estimation of where you would need to go. And keep in mind, that's still at this very slow operation of 3 milliseconds, right? So if we could run it faster, then we can get the compute done quicker and we will burn less power in that time step. So the question is, could you run these things faster? And I'll take a little side detour and talk about that in the devices. So it turns out that you have a lot of design parameters in the OECT device. There are some models of their operation. One's called the Bernard's model that came out of George Meliaris's group, and we've adapted that for some of our work. But what it shows is there are different regimes of operation for the OECT. So in this case, the x-axis here is time, and you notice this is very slow. And the y-axis is either the gate voltage in this case, or the drain current. And so you could apply a step function in the gate voltage and then see some evolution of the current, either asymptotically going to the saturation value or a spike in recovery position. And that's what the original Bernard's model had predicted based on more or less a capacitive model of the dynamics of the system. So we dug into that a bit deeper and started to look at really modeling the different time dynamics inside the device, in particular looking at the different capacitance of drain, source, and gate, and what the field strength was at each one of those electrodes. And it turns out there's an intermediate case between the spike and recover and the asymptotic behavior where those kind of balance out. And you get the fastest time dynamics at this sort of magic point where the drain voltage is proportional to some geometric factors of the device divided by the channel capacitance. So at that specific drain voltage, then you get this more or less instantaneous, quote, instantaneous rise in the source current. In this case, so we went from, operation of milliseconds or longer to about 20 microseconds. So now if we can operate in that region of the device, we can run this thing at 20 microseconds. Still painfully slow compared to anything you would normally consider a computer, but it would vastly improve the energy efficiency and also give you a reasonable runtime. So, this is far from the final answer. You could do much better. You could shrink the devices down, have smaller capacitances. There's a lot more to be done here. But this just illustrates that there are pathways to very small power consumption and very fast operation, or reasonably fast operation. Now, we can also simulate if we put the OECTs in the reservoir. So before I showed activation functions like hyperbolic tangent or the swish function, but what if the activation function is the functional response of the OECT, right? The transistor response. And that's what we would build to make the transistor. So you can write out all the transistor equations. Obviously not going to go through these. I think would put everyone to sleep, but you can build in these dynamics into the network simulation of the reservoir. And this turns out to work pretty well. So we trained it up on just like a simple series of time steps. So we just input into our reservoir, again, this is all simulation, just step functions, and ask the reservoir to learn those dynamics. And it was able to mimic it pretty well. Sometimes the decay constant is off a little bit, but it gets the transitions right. Oh, and this was, we trained it on experimental data. So the actual shape, we're trying to get the actual shape close to the experimental shape. So then we put that into prediction of the Lorentz system and compared it to what would be a normal hyperbolic tangent activation function. And we find that the prediction times in this case were about the same. So this is the root mean square error for the prediction time, and the OECT case versus the baseline hyperbolic tangent are about the same. But the point is you can do it with a smaller number of neurons. And so this is like a small slice of the larger study that I showed before. But in the OECT case, you can use maybe as few as 10 neurons. And that would give you a RMS error of like 0.5, but that's way better than the baseline case. So there's something about the information complexity of the response of the OECT that gives you better performance of the reservoir computer. So we haven't quantified that yet. We haven't done the level analysis with this response function that we did before, but it looks promising for the OECT. So basically the standard activation functions, hyperbolic tangent and ReLU, are probably not the best for reservoirs. Okay, and I'll just bring it to a close here and talk about how we might physically make these. And this is work done in collaboration with Robert McCurdy. He's in the mechanical engineering department here. And we've just gotten started, so we don't have full results here, but the goal is to be able to print these things using inkjet printing and to print multi-gate OECTs. So in this case, you're seeing a source and a drain and a single gate. We could put 2 gates on this device. And then if you are tricky, you can get multiple gates by wiring off to other sides. You can think about different geometries for this. This is also done in a hydrogel as opposed to a purely liquid electrolyte. So the hydrogel gives us something that's less volatile and is more or less stable in room conditions. Of course, mechanically flexible and so forth. If we want, we can then wire it up to conventional electronics. This looks quite ugly, but this would be academic level integration of those OECT arrays into DSP chip or just simple op-amp chips. And just to show that this can work, these are some of the performance curves for the multi-gate OECT with a hydrogel electrolyte. And it's not obvious that the hydrogel would work because the ion diffusion is a lot slower in the hydrogel, but it does work reasonably well. You can get something that looks like a standard transistor function at different gate values here. Not perfect saturation, but more or less works well in the triode regime, the linear regime of the OECT. And then more recently, we also using ionic liquid instead of the hydrogel. That works out pretty well also. So you see reasonable transfer curves from the ionic liquid. So these are all an attempt to make something that is stable at room conditions, so the electrolyte doesn't just boil away. It also allows us to print devices vertically. And I'm not showing that, but Rob's group has done that by printing a couple devices on top of each other and building up in the third dimension. And so now we can think about not just a 2D array of OECTs, but something approaching a fully 3D array. And that opens up more complex topologies and a higher density of compute elements that you would use for your reservoir. So actually, that is all I had to say. I just wanted to highlight the story for everyone. I want to thank my PhD student, Lauren, who's done all the simulations, previous student, Jake, who had started the project. He's now off in industry. Student in the group of Professor Juan Restrepo, who recently graduated, is now doing a postdoc at Vermont. And then Venkata, who is doing the printing of the devices in Rob McCurdy's group. And this is supported by internal funds by the College of Science, the Renewable Energy Institute here that I'm sitting in, and then Department of Energy is funding Lauren Hurley's work. So yeah, that's the story, and I'm happy to take any questions. Thank you for your time and attention.